The continuation of our deep learning tutorial series. And the last time you remember we learned about how to upgrade our univariate linear regression problem to a multivariate linear regression. Now today we shall be looking at logistic regression, and this is just a recap of our linear regression problem in neural network. And this is the code which we have gone through. We talk about the multivariate. We went through all this, that we need to draw an hyperplane when you have more than one features. We went through all this in the last tutorial, and we talked about the equation that we need to learn when we have more than one variable. And we say, how do we choose our W using gradient descent, and how we can actually calculate the total error based on our actual prediction, and based on our prediction and the actual values of y. You see how gradient uses partial derivative based of each of the parameters to be able to take a step towards the global minimum. You see that we have to do a simultaneous update, and we have to choose a learning rate that determines how far we take our steps. And we discover which are typical examples of learning rate values that we can start with to be able to see our model prediction does, and what's the error rate, and what is the performance of our models. Now essentially, when we have when we're training our models, we expect that the total error should decrease steadily. It should decrease steadily as we proceed the iteration. Remember that the cost function is the same thing as loss function or the objective function. Now, one of the ways by which we can actually get our deep learning model to be a neural network model to actually perform very well, for the error to decrease steadily, is by doing what you call feature scaling. So feature scaling is when you have more than one variable, the values of each of the variables can vary significantly. So we want a situation whereby the values between the variables will actually be within the same upper and minimum. For instance, if we go back and check here, you see that the maximum and the minimum values in the number of bedrooms might actually be, minimum can be 1, maybe maximum like maybe 5. But when you look at the square feet, you see that the range of the numbers here are quite high compared to the range of these numbers. Our model will not do very well when you have features that are actually having one very big values on values in one particular features, and another one have very small values and see as very small values. So these are not normalized. So when we have something like this, we want to make sure that we normalize all our features so that the algorithm will be able to converge easily. And that is what this is trying to do, by what to say that we do a feature scaling, and ideally what we want is all the values in the feature to be between -1 and 1. And gradient descent can take a long time to find the global minimum if you don't do that. So for instance, like I explained, this one is in this range and this one is in this range. So we need to do feature normalization. We have seen this before. It's our target to be able to move and get our network to be able to achieve an error that is towards this point, the total errors to be minimized towards this point. And so this is our parameters W1 and W2. So we have seen this before, that when we have more than one variable, this is how to expand our network to be able to, neural network, to be able to capture the additional variables. Now, today's work is for us to focus on logistic regression. And I always use this C to be able to remember that this is a classification problem. Classification means you're trying to actually predict a class. You're trying to you have what you call discrete number, discrete values. You have discrete values. You have a category that you actually want to predict, whether true or positive or negative, or whether yes or no, kind of thing. So in linear classification, you have what you call the discrete number of classes. So this is ck, where k will be the number of classes, maybe 2, 3, and so on. So now the input space is divided into decision region whose boundaries are called decision boundaries, which you can say you can group some data points and say, okay, they belong to a particular class, and you have another set of data points and you say that they belong to another class. An example of binary classification, that means you have two. In this case, that means our k is equal to 2 because you are putting them into two classes, spam or not spam, malware or benign. Now, in linear regression, you remember that when we want to model our function in linear regression, when we're trying to model our hypothesis, we essentially use this in linear regression. Now, in classification problem, we want to predict discrete class labels. So we're not predicting a number, unlike in linear regression. So for us to be able to do that, then we have to bring in a notion of probabilities. So more generally, possible probabilities lie in the range of 0 and 1. So the values that we want to predict, we want it to be between 0 and 1. So we can say, okay, all that are in the zeros, they belong to 0 class, all that are in 1, they belong to 1 class. So generally, linear model transform the linear functions of W using a non-linear function. Now, so we now have our prediction like we have in linear regression, but this time around we need to pass our predictions into another function, and this is a sigmoid function, also called the logistic function. And what the sigmoid function does is it squashes whatever values that we get from this computing, it squashes them into between 0 and 1, and ensures that they are between 0 and 1. Then we can now make a decision that anything that is below 0.5 belongs to 0 class, and otherwise. So this is our formula for our logistic regression, or what you call the sigmoid function. It takes in a variables, and this is the definition: 1 over 1 plus exponential negative z. Now, since in this case our z will be w transpose times x, so we can just substitute the z in this place with w transpose times x. So the z will become w transpose multiplied by x. Alright, so what are the properties of the sigmoid function? It is that it is symmetry. When you put in a value, a negative this into this, is the same thing as saying putting in a positive value into that and saying 1 minus that. It's inverse, that is a logic regression. That is, you have the ln of this, its inverse is this, that is the inverse of that, and the derivative, if you do a derivative of the sigmoid function, this is essentially what you are going to have. So these are properties, mathematical properties of the sigmoid function, or what you also refer to as logistic function. So I've explained this before, so you just substitute the values there with a z. So this is now the representation for our logistic regression. Now, what then we do is that once we have computed this, which is going to give us a value, because of we are passing through sigmoid function, it's going to give us a value between 0 and 1. So what this then do is that we can now say that the probability that y equals to 1 given x and w, which are the inputs to the sigma function, and the probability that y equals to 0. So if you actually get our hw of x to be the probability that y equals to 1 given x and w, to be able to get the probability that y equals to 0, we just say 1 minus whatever we have gotten for y equals to 1. So logistic regression, you can look at it as a probabilistic discriminative model. It models a conditional probability where this is the condition. We're trying to get the value of y knowing the value of x. So the decision boundary. Now, how does the decision boundary look like for logistic regression? Like we have said, we decide what our decision boundary is going to be. We can decide that, okay, if the values that is predicted is greater than or equal to 0.5, then we say that means our probability is y is 1, and otherwise we say y is equals to 0. So now the decision boundary is linear. Logistic regression is a linear classifier, although it is possible to be able to kernelize it and make it non-linear. Now what this is saying is we are actually trying to learn the decision boundary. That is, we want to try to draw a line between the two classes. This is one class and this is another class, and we're trying to line a line that neatly separates this one class from the other class, and that is essentially what this is going to be doing for us. By the time we squash the data, our prediction into those that belong to 0 and 1 based on this threshold, that can help us to be able to draw a straight line between the two classes. So next time we're going to start with the cost function, because the cost function helps us to be able to know how to minimize the parameters to be able to reach the global minimum. Thank you. Do let us know what your comment are. Thank you.